Ram Bhimashankaram 8.6 Jordan Canonical Form, or JCA for short. Now, Jordan Canonical Form is definitely not a topic that one should spend too much time on during our first course. And we shall not really follow Ram Bhimashankaram 8.6, where they will give a proof completely devoid of all motivations of the Jordan Canonical Form. Instead, we shall merely state what it is, why it is important, and some interesting ways one can use Jordan Canonical Forms even for elementary linear algebra. We have seen this diagram in this video series earlier also. So this is like a black box into which you feed a linear transformation from Cn to Cn. You can represent it as a matrix, n by n matrix over the complex field. However, in order to do that, you have to pick some basis, any arbitrary basis of Cn. So this matrix will represent the linear transformation with respect to this basis. As a result, in the properties of the matrices will be mixed. Some properties which will be due to the linear transformation and some property which will be due to the basis. And we are interested in only finding those properties that are properties of the linear transformation alone. Now for that, we notice that if I change the basis without changing the linear transformation, the matrix changes by a certain rule which is called Similarity Transform. So if A is the matrix for some linear transformation with respect to some basis, and B is the matrix for the same linear transformation with respect to possibly some different basis, then A and B are similar matrices and they are related in the following way. B is equal to PAP inverse for some non-singular P. So the natural question that we ask is that when are two matrices similar? So far the way we have used this is by saying that we will be interested only in those properties of a matrix that are preserved by similarity transformations, but there is a deeper, more abstract question that is also there, which says, given two matrices, how do I know that they are similar? Obviously, you cannot keep on taking all sorts of non-singular matrices P and checking if PAP inverse is equal to B or not. So is there some nice way by which we can do this? Now, compare this with the example of fraction. Then I know that this fraction and this fraction are the same. Now, how do I check that these are same? One way is reduce both of them to their simplest form. In that case, you will see that their simplest forms are the same. Hence, I can say that these two fractions were actually the same. Now, can we get some such simplest form such that given any matrix A and any other matrix B, square of same size, I can reduce A to that simplest form and reduce B to that simplest form. And if they are indeed similar, those two simplest forms must match. So I need an if and only if relationship. Now much of development of linear algebra is motivated by trying to find such a necessary and sufficient conditions. And the list of necessary conditions has grown and grown and grown and include trace, determinant, rank, eigenvalue, characteristic polynomial, algebraic multiplicities, geometric multiplicities, minimal polynomial, and maybe some other things. All these things are necessary conditions, which means that if two matrices are similar to each other, A and B are similar to each other, I am using this little tilde symbol, not a standard notation, then trace of A must be trace of B, determinant of this must be determinant, etc., all these things, but not a single one of them is sufficient. In fact, all these things put together is not sufficient. So, if I have two matrices A and B such that their traces match, determinants match, ranks match, eigenvalues with algebraic multiplicity and geometric multiplicity match, characteristic polynomial matches, minimal polynomials are also the same, but even then it is quite possible that A and B are not similar to each other. So naturally people try to look for some criterion such that it will give you an if and only if way of checking whether two matrices are similar. Now, the final answer to that was the Jordan canonical form. So Jordan canonical form of a matrix for the time being is something. It is something like a reduced form of that thing, such that if A and B are similar, they must have the same Jordan canonical form, and conversely, if the Jordan canonical form of A matches Jordan canonical form of B, then A and B must be similar. So the first importance of Jordan canonical form is providing an affirmative answer to this long-standing question of how to check similarity of two square matrices of the same size. To understand the concept of Jordan canonical form, we have to understand a concept of Jordan block. Jordan blocks are square matrices of this type. They are upper triangular. All their diagonal entries consist of the same number. We are always working over complex fields, so all these things are complex numbers. And the numbers in the diagonal entries above the leading diagonal, they are all ones. So there are, in this case, I have taken a Jordan block of order 4 by 4. So there are exactly 3 ones. All other entries are 0. So the simplest Jordan block is, of course, just a scalar itself. It is a Jordan block of size 1. So I do not have any additional 1. If it is of size 2, then it will be like this. And you will recall that in our video, we have often used this particular matrix as counterexamples for various things. That was basically a Jordan block of size 2 with diagonal entry given by 1. The diagonal entries could very well be 0, but all the diagonals must be the same. Now we have seen earlier that any semi-simple matrix is similar to a diagonal matrix, and any square matrix is similar to an upper triangular matrix. Now semi-simple matrices are very special types of matrices, and this was kind of it did not have much structure. Upper triangular, so there are so many possible entries, so it was too little structure here. And here we have lots of structure, very nice, but it is very restrictive, it is not general. So Jordan blocks sort of come in between. They are upper triangular, but in a very structured way. They are basically like a triangular matrix, except for one thin layer of super diagonal entries, which are all 1. So the result basically tries to say that any square matrix can be composed of only Jordan blocks up to similarity. So now we are in a position to give the precise definition of Jordan canonical form. It says that any square matrix over the complex field is similar to a matrix like this. Now this matrix is an upper triangular matrix where each of these things is a block. It's a Jordan block. Remember that a Jordan block is completely specified by its order and the diagonal entry. For example, this one says it's a Jordan block which is n1 by n1, and all the diagonal entries are lambda 1, lambda 1, lambda 1. Similarly, this is another block, another block. Since these things are actually upper triangular matrices, so the entire matrix is upper triangular. So this is very much like the theorem that we had earlier, that any square matrix over C is similar to an upper triangular matrix, except that now we have put a very special structure to the upper triangular matrix, which gives rise to this particular result, that it will be unique up to similarity. So this says that anything can be represented in this way. Now I am not going to prove this result here, I am merely stating it. Say for example, one such matrix could be like this. Here all the entries that I have not shown are actually equal to 0. To recognize that this is in this particular form, you observe these ones. Observe that there is no 1 here, which means I have to consider these as one block. The ones will tell me where I create the block. 2 ones means there is one 3 by 3 block. No 1, which means 0 many 1, so there is a block of size 1 by 1, and then there is another block of size 2 by 2. So I have got 3 blocks. Notice that the lambdas need not be unique. I have 2 here as well as 2 here. So this is a matrix like this. So this is what is called the Jordan canonical form. So again, given any square matrix, you can write it in this way. So we shall say that this is Jordan canonical form of that square matrix. Now, is this unique? Well, not really, because whenever you are talking about just similarity transform, you can always have some ability to just permute things around. So we cannot say that these things are all unique. Now, in fact, you can strengthen this result by saying this is actually unitarily similar. That is, the matrix with which you will do the transformation will be a unitary matrix. Now, I am not going deep into the statement or the proof, but the main idea is that any square matrix is basically a bunch of these Jordan blocks, and you cannot say the first Jordan block or the second Jordan block because their order does not matter. However, if I consider them as a basket, in that case, that basket content will always be unique as long as you are working with matrices that are similar to each other. To understand this, suppose I have two matrices, both of them of the same size, n by n, and you find out Jordan canonical form, which is not unique, but unique up to the placement of the boxes. So consider this as a big basket, you possibly see that there is something which is J2, 5. Then there is one J1, 6. Possibly you also have J2, 6 also. Maybe yet another copy of J2, 5. So the same block may repeat a number of times. So it consists of only these 4 blocks. This has been repeated, these are all separate. Now, if you consider the basket here for B and you find that you have precisely the same things here also, then A and B must be similar. And conversely, if A and B are similar, then their contents of the two baskets must be the same. If on the other hand you have something say missing, you have J15, the moment you have J15, without even looking at what are the other things, you can say that these two things cannot be similar because J15 is not found in this basket. So that is the power of Jordan canonical form. Given any two matrices, find their Jordan canonical form. Don't worry about the order in which the boxes come as a result of whatever algorithm you are using. Merely count the boxes and put them in a basket. Do the same thing for B and check the contents of the two baskets. They are same if and only if the original two matrices were similar. Now there are algorithms by which you can find Jordan canonical forms. However, they are not that popular simply because Jordan canonical forms theoretically are nice objects, but practically they are not very nice. Though you can find so many interesting things from them, usually there are straightforward direct methods of obtaining those interesting things which are a lot less computationally expensive than finding the Jordan canonical form first. However, theoretically it is of great importance because, for example, I have this particular thing in my basket. So I have got these blocks. As I said, the order is not important. You can read off all the different invariants that we discussed earlier, things like rank, trace, eigenvalues, and etc. from this. Now, these things are the diagonal entries and these are the orders. So from this, I can quickly see what are going to be my eigenvalues. I can see that they must be 5 and I. So I can get my eigenvalues. Suppose I want to find out the algebraic multiplicities, which are very easy. Just count how many times I occurs. How many times? 4 here and 3 here. So algebraic multiplicity of I is going to be 4 plus 3, and that is equal to 7. Similarly, algebraic multiplicity of 5 is going to be 3 plus 2, that is 5. How can I find out geometric multiplicities? A little bit of thinking will tell you that number of blocks, number of Jordan blocks for a particular eigenvalue will give you that. So in this case, there are 2 blocks, so that number is 2. Similarly, for 5 also, the number happens to be 2. So you get the geometric multiplicities. Now, interestingly, this immediately tells you that geometric multiplicity must be less than or equal to algebraic multiplicity, because the smallest size blocks that you can get will be just 1 by 1 blocks. So the total number of blocks can never exceed the total number of diagonal entries that you have. So obviously, GM must be less than or equal to AM. So once you have Jordan canonical form, all those theorems just follow in 1 or 2 line arguments. But of course, proving Jordan canonical theorem in the first place takes a lot of work. Okay, now suppose I want to find out it's a characteristic polynomial, which is pretty trivial because I can see algebraic multiplicity, so it will be lambda minus I to the power 7 and lambda minus 5 to the power 5, nothing very profound here. Suppose I want to find the minimal polynomial. The minimal polynomial may be obtained like this, lambda minus I, and you will raise it to the power of the maximum sized block. Here out of these two, 4 is the maximum size, so it is 4, and similarly lambda minus 5, the maximum size of this is 3, so this is going to be the minimal polynomial, and it is pretty straightforward to check why this is going to be the case, and this also shows why minimal polynomials do not guarantee that two matrices are similar. That is, if two matrices A and B are actually have the same minimal polynomial, still they need not be similar. If I ask you to come up with a counterexample, in general that will be quite tricky. How can you come up with two matrices that have the same order, both square, both have the same minimal polynomial, yet they are not similar? But now that is quite easy, because in one case you will just take something like this. So you will take a matrix where you have these as your Jordan blocks. So in this case, I have eigenvalues 1 and 2. And its minimal polynomial will be lambda minus 1 to the power the maximum here, and lambda minus 2 to the power 3. Okay, I will put one more thing. This times 1, 2. So it still remains the same. Okay, now what I will do is I want to create another polynomial, another matrix of the same order, such that all these numbers still will add up to 5 plus 2 plus 3 plus 1, which is 11. So I still want this to be 11. But the maximums will have the correct orders. So what I will do is this, I will keep this 5 as it is. Instead, I will make this 1, which will not change this 5. But since I have reduced it, I have to increase that. Can't increase this because then this will increase. I will make this 2. So I get two different baskets and both of which I will actually get the same minimum polynomial. Now, Jordan canonical forms also help to explain how rank and number of non-zero eigenvalues are actually related. So you can check quite easily how number of non-zero eigenvalues is actually less than or equal to the rank. So you can just take that as an exercise yourself to see how these things are related. So in this way, if you assume Jordan canonical form, then many of these results become very obvious and they come on a common footing. So if you want to quickly generate counterexamples for some result, or you suspect that something may be true and you want to quickly go through a number of examples to see if you can generate counterexamples, then Jordan canonical forms are a great way to go.